Hello everyone, and thank you so much for joining this webinar. My name is Valerie Padilla, and I'm a technology strategist in the server CTO at Dell EMC. Today I'll introduce you to GENZ, tell you what it is, what problems it solves, and what are some of its high-level attributes that make it a powerful solution for next-generation infrastructure. In order to do this, I need to take a little step back and set the stage on the motivation behind GENZ and some of the challenges being faced in the IT industry. We have more data than ever. The data explosion problem is obvious to most of us, especially with our love for social media and all of the personal content we're generating every day. And this data is going to continue to skyrocket, especially with the Internet of Things, or IoT, which is an emerging field where these devices will be monitoring and in control of everything from appliances, security systems, transportation systems, and so on and so on. Well, it's obvious that the amount of data being generated, stored, and analyzed in the next generation infrastructure is going to be phenomenal. This massive increase in the amount of data being generated is one thing, but what we're finding is that an estimated 37% of all data generated will have some sort of significant business value. And that leads us to the chart on the right, which shows the need to analyze the data even faster than ever before to provide real business value and insight from the data being collected. The data needs to be analyzed faster than ever since the value decreases over time. So as the old saying goes, time is money. These two trends multiply the challenges for today's infrastructure to deliver the business results required in a timely and cost-effective manner. For an example of the stresses these trends have on today's infrastructure, we can take a look at the evolution of the traditional two-socket server over the last few years. In 2017 to 2019, we see CPUs that support 8 DDR channels per CPU socket and 64 or more PCIe lanes per CPU. In this case, most of the PCI expansion is to support the requirements for greater numbers of NVMe drives directly connected to the CPUs. In this time frame, PCI Gen 4 will emerge. All of this memory and I/O bandwidth is necessary to support the continuing rise in the CPU core counts. At this point, we see that processors are well over 4,000 pins, and their size, complexity, and cost continue to rise. On the horizon, we see another generation of interconnects and bus technologies coming up, including DDR Gen 5, SAS and SATA Gen 4, and others like GPU and coherent interconnects, like CXL and OpenCAPI. We have an ever-increasing amount of protocols and interconnects being used to connect components in our two-socket server. As these boards add these faster and more complex technologies, the systems are becoming much more complex and costly to manufacture. To highlight the trends we saw on the last slide, this chart helps us visualize the challenges that processor architectures face. The graph on the left is a normalized measurement of several properties of a typical server-class CPU, where the vertical axis shows how much of an increase in each property occurred from 2012. From this graph, we can see that over the last several years out to 2019, there was a significant rise in the number of DDR channels and PCI lanes on these CPUs. Factoring in data rate increases, the total bandwidth of each of these would be somewhat higher, but not by much. You'll notice that we pay a price in the number of CPU pins required to maintain these increases in memory and I/O bandwidth. Over 4,000 pins will be common in the near future. This graph also shows that the CPU core counts are growing astronomically, while the memory and I/O capabilities of these same CPUs is going down. The trend is undeniable. Even though the CPUs are becoming more powerful, we literally cannot keep the CPU cores fed with the data as well as we used to, leading to more CPU stalls and lower CPU utilization. These trends are not sustainable. There needs to be a better way to get the processors that data quicker. Beyond the internal interconnects within a server, the way that servers are connected to share data and work together to perform workloads is also facing challenges as we look to the near future. Today, several different fabric and networking technologies are used to connect servers and data storage systems together. We have Ethernet as a general-purpose network, Fiber Channel, SAS, and SATA for block storage connectivity, InfiniBand and OmniPath for high-performance computing and low-latency messaging, and even PCI Express is used in limited circumstances as a fabric technology. But each of these were created for specific purposes, and none of them behave as a true memory semantic fabric, to speak the native language of the CPU, which is load-store, read-write, reading and writing bytes and cache lines at a time instead of blocks or messages. The ability to be a memory semantic fabric is critical when we move from block and file and object-based storage to memory-based storage with the help of byte-addressable persistent storage class memory, or SCM. If we take these network and fabric protocols and add them to our list of the internal server interconnect protocols, what we have is a tower of protocol babel. Every time data is moved and converted from one protocol to another, this adds complexity, power, cost, and management overhead. There has to be a better way to evolve this infrastructure to become something more streamlined and optimized for the memory-centric computing model of the future. Here's a picture of the different classes of memory and storage technologies in use today. On the left are the internal processor registers or memory blocks with sub-nanosecond access latencies. Then there are the integrated or external SRAM devices, typically used for caches that operate in the 5 nanosecond or less latency range, but still have very low load-to-use latency. Next is DRAM, which is typically external to the processors with higher latency in the 100 nanosecond range, but still provide excellent low-to-use latency on average when placed behind cached memory. All of these memory types are byte addressable and volatile, which means your data does go away when the power does. On the right-hand side of the chart, we have the persistent memory technologies that are accessed as blocks of data, and they typically have much higher capacity and higher latencies than volatile memory types. Flash memory, like what we have in our SSDs, is fast by storage standards at 100,000 nanosecond access latencies, but this is super slow compared to our volatile memory types. Traditional hard drives and tape drives round out the block devices category, but the access speeds here are glacial compared to our volatile memory devices. Storage class memory is an emerging technology that looks to bridge the gap between these two classes of memory. It has both persistent and byte addressable properties, and their latencies are somewhere between DRAM and flash memory latencies. As storage class memory matures, the access latencies will continue to get closer and closer to DRAM latencies, and will eventually provide a near memory alternative to DRAM technology. At this point, storage class memory provides the best of both worlds and offers a vision to memory storage convergence. This evolution will drive a new class of computing that's often referred to as memory-centric computing. Let's go back to our server architecture picture and see where we can place storage class memory. First, we can place storage class memory on the PCIe bus. Typically, this is in a storage class memory PCIe card plugged into a PCIe slot, as shown in the picture. A storage class memory PCIe card offers good capacity and decent performance for early storage class memory technology that has higher latencies. It's an industry standard form factor, which is also a positive. However, this option limits the locations where the storage class memory can be placed due to strict PCI bus routing rules. And this limit will become much more challenging as PCI Gen 4 and Gen 5 are introduced. In addition, the PCI bus is not built for reliability, where multiple links or paths can be deployed to ensure memory connectivity. Also, the PCI cards are stranded resources on the local processor, which means the storage class memory cannot be accessed from any other server. Sharing the memory requires more complex protocols like Remote Direct Memory Access, or RDMA. Another possibility is to place the storage class memory on the processor's DDR memory channel in one of the DIMM slots. Persistent memory DIMMs are commonly called NVDIMMs, short for non-volatile DIMMs. One class of NVDIMM uses DRAM memory that's backed up to flash if power is lost. These DIMMs are called NVDIMM-N and typically have lower capacity than standard DIMMs because of the persistency circuitry, but they're very fast and operate well on the DDR channel. Another type of DIMM are NVDIMM-P DIMMs that utilize storage class memory natively. These DIMMs have logic that allow the storage class memory to operate on the DDR memory channels. NVDIMM-P have good capacity, although not as high as PCI cards. The challenges with NVDIMM-P is that the CPUs have to be made to slow the DDR channels down to allow the slower storage class memory to operate correctly. This also eliminates the ability to share the DDR channel between NVDIMM-P and standard DDR DRAM DIMMs. This means that we're sacrificing precious DRAM memory channels for the capacity and persistence of storage class memory. So storage class memory is not a great fit for DDR memory channels, as placing them there is somewhat unnatural. Storage class memory on DDR channels also suffer from the same reliability problems that PCI does, but even more limited placement restrictions of DDR DIMM slots. Finally, storage class memory on the DDR channels are also stranded and can only be accessed by the local processor and cannot be shared by other servers in a byte addressable way. So what's the solution to all of these challenges? It's GENZ, the Universal System Interconnect and Fabric technology that's built from the ground up to be open, high performance, reliable, secure, flexible, compatible, and economic. GENZ can power the next generation of memory-centric computing to deliver the workloads required well into the future. First and foremost, this technology must be open. We want the IT infrastructure, component suppliers, and the IT community to all be participants in the definition and implementation of this technology. So it's universal and operates in many different market segments across a broad range of workloads. It must be high performance, high bandwidth, low latency, and scale from motherboard to chassis to rack scale. Bandwidth to feed the ever-increasing core counts and processors of the future, but more efficiently with less power and lower cost. It must be reliable and secure. If we're connecting persistent memory to a fabric to be shared by many processors, it had better have rock-solid reliability and secure enough to prevent malicious accesses to business-critical data. It needs to be flexible to be able to implement this technology in as many places as possible throughout the infrastructure. It needs to be able to allow SoCs, CPUs, memory and I/O devices of multiple generations and types to be connected seamlessly together. It needs to support direct attachment of SoCs to memory and I/O, as well as enable a fabric where multiple SoCs can provision and share memory, accelerators, and other I/O devices dynamically. It must enable compatibility with existing unmodified operating systems and applications so they can take advantage of the new infrastructure built with this technology. It needs to be economic and provide greater workload efficiency to achieve dramatic increases in data processing, get business-critical answers much faster, all without an equivalent increase in costs. The GENZ consortium was announced in 2016 and has grown from about 12 members to now at a little over 65, and the membership includes everyone from processor vendors to silicon, software, OS, connectors, just everything we'd need to really have a vibrant ecosystem. GENZ allows any device to talk to any other device as if it were talking with its own local memory, using simple commands, sometimes called load store access model. We refer to it as being memory semantic, and what that means is it speaks the same language as local memory does today. And how does GENZ do that? Well, today we have a memory bus that sits between the processor and the memory, and that processor only knows how to speak a certain amount of languages. So it only knows how to talk to certain types of memory. And the reason is because the media controller is integrated into the CPU, making the CPU and memory interlocked together. That means when new memories come out, if they have slightly different interface needs, I can't talk to them. I have to wait for another processor spin. GENZ says there's a better way. Let's take the media controller and put it where it belongs, and let's put it right next to the memory. And then let's use GENZ as that link to get between the processor and the memory, so it's very simple for you to change the memory on the outside. And it can be any type of memory that we need. If you need a type of memory that's completely unique to you, it's available. It also allows for that media controller to start to do some of that compute. This is how we can feed those CPUs the data much faster. This change allows us to do two important things. First, we unlock the lockstep innovation between CPUs and memory, and the CPUs and memory can evolve completely independent of each other. Second, we can now support a wide range of memory technologies, which is especially important for storage class memory, where there are many variants with different attributes that may be required for different workloads. A CPU or SoC can support memory generations and types that weren't even comprehended in its original design. This capability enables a new level of memory and system innovation. In the next set of slides, we'll focus on the key attributes that were used to guide the design of the GENZ protocol and architecture. GENZ was designed to be a high-bandwidth universal system interconnect. It handles load store memory accesses, block access storage, and messaging. The chart on the upper right shows full duplex aggregate bandwidth in gigabytes per second for several different GENZ configurations at varying numbers of lane pairs and lane data rates, where a lane pair is one transmit plus one receive lane. We'll consider two scenarios that represent how GENZ may be introduced in a typical server deployment. Initially, GENZ will not be integrated into the CPU, but will use an external bridge that provides connectivity between the CPU's high-performance cache coherent links and the GENZ links to the rest of the system. A typical bridge configuration would be 32 GENZ lane pairs and supports either 25, 32, 56, or 112 gigatransfers per second data rates, depending on the generation of technology and workloads being targeted. The bandwidth that can be achieved with the solution are illustrated in the four leftmost bars in the chart. The GENZ links can support byte addressable memory, block access storage, I/O to accelerators, and messaging to other servers through external GENZ fabrics. Although DRAM is shown, storage class memory will be more common as a byte addressable memory for an external bridge. If the solution requires more than 32 lanes, adding external GENZ switches to expand the connectivity will be common. Over the course of time, GPUs or other system-on-a-chip or SoCs will integrate the GENZ bridge logic to provide native GENZ link support. In the picture, we see how this integration transforms, simplifies, and expands the GENZ connectivity of the CPU. Now the number of GENZ lane pairs that the CPU supports can double or more. We demonstrate this by using 64 lane pairs for a typical CPU configuration, which corresponds to the rightmost bars in the bandwidth chart. Integrating the GENZ logic also enables the very highest bandwidth and very lowest latency. For those of us who prefer to see bandwidth numbers and networking terminology, here's the same chart that uses terabits per second for aggregate bandwidth. Based on the roadmap of linked data rates, you can see that GENZ offers the bandwidth necessary to feed the hungriest workloads in these high core count CPUs. GENZ also offers high-performance, low-latency access to byte-addressable storage class memory. This storage class memory can be connected directly to a processor or as resident on a GENZ fabric, to which processors are also attached. This is accomplished using technology that's already being implemented in operating systems today, the Persistent Memory File System, also known as the Direct Access File System, or DAX file system. This software was developed for use with NVDIMMs, so that they did not have to be treated as storage devices with all of the storage software stack overhead. The file system enables applications to use a modified file access API to have file data directly mapped into its memory space, so that it can be operated on using CPU load store byte addressable instructions for incredibly low latency file data access. By simply using a GENZ storage class memory driver instead of an NVDIMM driver, GENZ attached storage class memory can take advantage of this technology with no changes to the operating system. The figure on the right demonstrates the stark difference in performance of block storage under a traditional software stack and storage class memory under the persistent memory or direct access file system. Let's say our application wants to access a couple of bytes at a certain offset in a file that hasn't been prefetched into buffer cache. In the case of a traditional storage software stack on the left, the access request initiates the execution of about 25,000 instructions on the CPU, while initiating a total of 5 different data buffer copies in the different layers of the stack. The same request initiated through the DAX file system initiates an execution of 3 instructions on the CPU and no data copies to read-write a small number of bytes directly from the storage class memory. And oh, by the way, we didn't make the timing of this slide unfair, because we'd have to wait all day long for the animation to complete if we were going to make this to scale. So GENZ enables low latency data access to storage class memory using operating system software proven for use with today's NVDIMM technology. GENZ offers a set of features that are critical to the proper handling of mixed-use load-store memory accesses, bulk data accesses, and messaging as a universal interconnect in Fabric. This is a fun slide because I know we're all familiar with being stuck in traffic. At some point, I'm sure we've all been in a situation where we're driving our car on a 2-lane road and we're in a hurry, and we get stuck behind one of those large dump trucks or a huge bus. It's frustrating, isn't it? Well, this is a lot like traditional networks today, where small, low-latency packets get stuck behind one or more large packets as part of a bulk data transfer. The larger the maximum packet size supported, the worse the problem. Once a port starts transmitting a large packet, if a small low-latency packet is ready to go, too bad. Just like our 2-lane road, traditional networks have always been challenged with mixed-use data access and messaging. These problems are compounded if we try to overlay CPU load store accesses to byte addressable memory over networks like these. GENZ, on the other hand, is effectively a multi-lane superhighway. With its multi-link and MultiPath technologies, GENZ effectively provides multiple traffic lanes through the fabric. In addition, each link supports up to 32 virtual channels that are individually flow controlled and can be used for quality of service and prioritizing traffic class, ensuring transaction progress at all times under any traffic condition. Also, GENZ utilizes a 256-byte maximum packet size, coupled with hardware segmentation and reassembly for large data transfers, to ensure proper interleaving of small low-latency traffic with large bulk data access operations. The figure on the bottom illustrates the fact that fabric management can provision combinations of links, paths, and virtual channels for different classes of traffic. In the figure, some of the lanes are dedicated to a mix of small and bulk traffic loads. This is shown on the lower 2 lanes going in each direction. In a similar manner, the top lane in each direction carries only bulk data movement. The reliability aspects of GENZ allow traffic classes to be assigned to more than one link, in order to enable alternate paths in the event of a link or component failure. In other words, there's no single point of failure. These slides give a sample of the kinds of capabilities that have been designed into GENZ to enable higher levels of system performance. GENZ offers the most flexible link configurations available today. First, a link can operate anywhere from 16 to 112 gigatransfers per second per lane. A GENZ link can be composed of 1 to 256 lanes, although 8 lanes will be a common configuration. GENZ can support both symmetric and asymmetric links, which is unique in the industry. The figures on the right help explain how symmetric and asymmetric link configurations work. The figure on the left illustrates several symmetric link configurations which have the same number of transmit and receive lanes. It illustrates a by 1, by 2, by 4, and by 8 lane pairs between two components. Symmetric links are good for general purpose use cases where the read-write bandwidth on the link is about even. The figure on the right demonstrates the difference between a by 8 transmit and receive symmetric link and a by 2 transmit and by 14 receive asymmetric link. Asymmetric links are beneficial if traffic flowing over the link is biased for reads or writes. For example, if a CPU is connected to a memory component and the workloads will be read-centric, where most of the data is sent from memory to CPU, then having a receive-heavy asymmetric link is important from the CPU perspective. From the memory perspective, this is a transmit-heavy asymmetric link. A GENZ physical interface can be designed to support dynamically configuring the links between symmetric and various asymmetric modes. GENZ supports both copper and optical interconnects. The core specification specifies a general physical layer abstraction interface to support a variety of physical layers. The GENZ physical layer specification calls out both PCI compatible physical layer interfaces as well as IEEE 802.3 or Ethernet physical layer interfaces. GENZ is a universal system interconnect. In the picture, we have an SoC that's connected to an external GENZ switch. Any type of GENZ-enabled component can be connected to any GENZ link. We don't have dedicated memory links or I/O links or storage links. Any link can be used for any purpose for access to memory, I/O, storage, or even another compute component for messaging or data sharing. This capability allows very fluid deployments. So if we have an I/O-centric workload, I can add more accelerators to my configuration. If I have a memory-centric workload, I could add more memory to the system. If I need more storage, I can place storage components on any available link. Basically, one architecture that can support a wide variety of deployment models and workloads. In other words, we can right-size the infrastructure around a common architecture, which is very powerful. GENZ's flexibility is evident in its support of a variety of topologies and scales of deployment. GENZ's flexible physical layer options enable GENZ to scale from a simple component-to-component interconnect in a local system all the way to rack or row scale deployments. The figures at the bottom illustrate the various scales of deployment that GENZ enables, along with the associated physical layer and topology options available. At the bottom left, we have an example of a local system depicting a server motherboard that has CPUs that connect to DRAM or storage class memory, using GENZ daisy chain topologies. The next figure is an example of a system in a chassis, or enclosure, where one or more CPUs, accelerators, DRAM, etc. are connected to a mesh fabric topology using GENZ. The third figure is an example of a rack scale deployment using GENZ as a traditional topology with redundant external GENZ switches at the top of rack. However, the mechanical structure presented is anything but traditional, in that a rack of universal slots is used to host CPU, GPU, FPGA, DRAM, or any other type of GENZ enabled modules. Finally, GENZ supports well over 200 million components on a single fabric, enabling a row scale deployment as shown at the bottom right. What this slide shows is ultimately, can I get to my data? GENZ supports daisy chain, multi-link, and MultiPath capabilities. The figures in the top row demonstrate traffic flow if all links are working properly between two components. The integrated GENZ logic within the components distribute the memory and I/O transactions across these links, load balancing the traffic according to policies established by fabric management. The figures in the bottom row illustrate the case of a link, component, or switch failure. Let's say one of the links goes down. The components will automatically load balance the traffic that would have normally transited the broken link and redistribute this traffic over the remaining operational links. This failure operation is performed completely in the GENZ hardware and does not require operating system software or drivers to provide this functionality, like a traditional LAN or storage network. Once the broken link is restored, the GENZ hardware automatically rebalances the traffic across all paths. This is a standard feature for GENZ, and so this capability is universal for different component types like CPUs, memory, storage, accelerators, etc. For fabrics composed of GENZ switches, this feature also enables a level of reliability not seen in most memory or I/O channel technology today. These are examples of just some of the GENZ features and functions that provide leading-edge reliability. For data-centric computing, we can place a variety of memory and compute components on a common fabric. The data stored in the memory will be operated on by the compute components. This environment can be composed of multiple workloads in a multi-tenant manner. The data stored in this fabric-attached memory needs to be protected with rock-solid security to prevent inadvertent or malicious access to data in various memory components, or even a specific region of memory component by unauthorized applications. GENZ offers many different security and partitioning capabilities. Today we'll focus on just 4 of these features that make GENZ secure. The first security feature is access keys, which allow GENZ fabrics to be logically partitioned where each component and each link can be associated with one or more access keys. You can think of access keys as like virtual LANs or VLANs in networking. Access key protection is enforced in GENZ switches, either those integrated to any component or standalone GENZ. The next security feature are memory region keys, which are designed to protect components that share their memory regions on a GENZ fabric. Typical components that share their memory will do so by sharing multiple memory regions to different components on the fabric, usually compute components. The use of memory region keys ensures proper partitioning and protection to prevent components from unauthorized access to memory regions shared on one or more fabrics. The validation is performed by the component that owns the memory resources, not the GENZ switches, as this was the case in access keys. GENZ also provides cryptographic security capabilities for authentication and anti-replay prevention. Components that require authenticated communication with each other will share a secret key called Transaction Integrity Key, or TIC. And finally, we have the anti-replay tag, which is used to prevent man-in-the-middle attacks where components may repeat previously sent packets to impair a target component. So when a component sends a GENZ packet, it can include one of these optional keys in the header. When the switch or component receives the packet, it validates that the target is protected by the same key present in the packet header. If they match, the packet is processed. If not, the packet is dropped, an access violation log entry is created, and a security event is reported to fabric management by in-band or out-of-band mechanisms. This enables fabric management to quickly identify the issue and determine whether it was an inadvertent configuration error or a malicious attempt to try to access the targeted data. These are just a sample of the features that make GENZ secure. We have to take IT customers on a journey from legacy infrastructure to next-generation infrastructure, possible with GENZ technology. This includes the ability for GENZ infrastructure to support existing operating systems with no modifications, except for maybe new drivers. First, let's look at block storage support for GENZ components. We can have GENZ SSDs that operate almost exactly like NVMe drives from a software and driver perspective. We'll call them NVMe drives. These NVMe drives take advantage of GENZ's logical PCI device capabilities that allow unmodified operating systems to use their PCI discovery algorithms to discover and boot from these NVMe drives. In the picture, you'll notice the GENZ block drivers fit into the storage stack for traditional storage drivers. The GENZ driver communicates through the GENZ hardware interfaces to the NVMe drives on the fabric. Now let's see how GENZ-enabled storage class memory is supported under unmodified operating systems. Operating systems have been adding support for direct access to persistent memory-based file systems over the last couple of years, primarily to support emerging non-volatile DIMMs. The recently developed persistent memory file system allows the use of special APIs between the applications and the persistent memory file system to directly access file data in a byte-addressable manner. The persistent memory file system is designed to work hand-in-hand with the block driver for the persistent memory so that traditional block storage APIs and applications can also access the data in the memory devices. So here's the good news. GENZ-enabled storage class memory can completely leverage this entire stack of software to enable both storage access as well as the new persistent memory file system enabled applications by simply providing a GENZ storage class memory driver in the software stack. Finally, GENZ enables messaging between GENZ-enabled CPUs using existing APIs and software stacks. GENZ supports the concept of an emulated Ethernet NIC driver that facilitate tunneling Ethernet packets over GENZ. The eNIC driver sits in the same place as a traditional Ethernet driver would in the TCP/IP software stack. The eNIC driver accepts Ethernet frames sent down from the stack for transmission and utilizes GENZ hardware capabilities to segment the packet into smaller GENZ packets. Likewise, the GENZ hardware and eNIC driver receive encapsulated Ethernet GENZ packets from the fabric and reassembles them into Ethernet packets and sends them up the protocol stack. This enables traditional applications designed to communicate over the sockets API to continue to benefit from the compatible communication models across GENZ fabrics. The picture shows the use of GENZ and a high-performance computing software stack using the Open Fabric Interface, or OFI, and libfabric framework with the GENZ driver to support HPC middleware like Message Passing Interface, or MPI. HPC messaging implementations are readily achievable. We mentioned GENZ's logical PCI device, or LPD, feature in the last slide. Let's take a closer look at this feature. GENZ's LPD utilizes two capabilities illustrated in the picture. The first is a component PCI structure that is in the GENZ control space of any GENZ component that wants to be discovered as a PCI endpoint by a host component like a CPU. This structure embodies the PCI configuration space of the equivalent PCI endpoint. For example, a GENZ NVMe drive that wants to be discovered by the host CPU's operating system as an equivalent NVMe drive would implement the component PCI structure in its GENZ control space. The second LPD capability is a PCAM logic block in the GENZ-enabled CPUs. On CPU boot reset, the BIOS or system firmware will perform GENZ device discovery, and for each GENZ component discovered with a component PCI structure would map this into the CPU's PCI bus architecture and program the PCAM logic block to enable standard PCI bus discovery of the GENZ components using PCI bus device and function number. The picture illustrates how the GENZ devices appear to the operating system. As you can see, the arbitrary GENZ fabric topology is flattened to make it appear that all GENZ devices are tied to a single PCI bus segment. In addition, only GENZ devices that have a component PCI structure are discoverable by a standard PCI discovery algorithm. Another feature is GENZ's PCI compatible ordering feature, which enables GENZ to maintain strict transaction ordering similar to PCI Express to ensure complete compatibility with PCI Express device drivers. GENZ's ability to support a PCIe compatible physical layer allows CPUs to be designed with interfaces that are bimodal and operate as either PCIe or GENZ links to the rest of the system. This enables a graceful migration path from PCIe to GENZ. The picture illustrates the progression of a system from a PCIe-only configuration to a mixed PCIe and GENZ configuration, and finally to a GENZ-only configuration, all while using the same CPUs but reconfiguring a subset of the links on each iteration. The gray links and slots represent PCIe, and the red links and slots represent GENZ. The progression can be achieved by using different risers in each iteration that change the slots from legacy PCIe CHEM connectors to GENZ optimized connectors. GENZ's adoption of leading industry standard high-performance serial physical layers leverages high-volume silicon libraries, which in themselves drive lower cost. Using this technology enables GENZ components to benefit from levels of pin efficiency not found in today's components, making them smaller, easier to manufacture, and lower cost. This also leads to the printed circuit boards that these components are mounted on to be easier to design and manufacture, further reducing costs. The figure on the left shows a state-of-the-art CPU-GPU, or system on a chip, with 8 DDR memory channels and upwards of 64 or more PCI Express lanes. You're looking at a device with well over 4,000 pins. 50% of those pins are just for the DDR memory channels, including power, ground, control, and data pins. The figure in the middle illustrates the pin efficiency of DDR5 memory channels versus GENZ interfaces at numerous data rates. Pin efficiency is the bandwidth of the interface divided by the total number of pins embodying that interface. The pin density of a DDR5 channel at 4400 megatransfers per second is about 0.55 gigabytes per second per pin, while the pin efficiency of GENZ at 32, 56, and 112 gigatransfers per second is 4, 7, and 14 gigabytes per second per pin, respectively. Obviously, a significant improvement. What this allows us to do is build new CPUs, GPUs, and SoCs with 4x to 8x the bandwidth, with 50% fewer pins dedicated to memory. This allows us to lower the device package costs and dynamically simplify the PCB design and lower overall system costs. GENZ has developed a connector specification. The pin density is 0.6 millimeters and much smaller than legacy connectors, but with excellent signal integrity characteristics, demonstrated with performance to 112 gigatransfers per second. This connector family supports vertical connectors of various sizes for both drive, similar to the U.2 connector, or cards, similar to PCI form factors. There's also a compatible right angle, straddle mount, copper, and optical connector as well. The strengths of this connector system have led to its adoption by the GENZ consortium. The spec has been donated to the SFF as SFF TA1002, which has been adopted by the Open Compute project for the 3.0 MES board and is being considered by other well-known industry consortiums. Enabling this GENZ connector family as a multi-purpose connector helps drive volumes and lower costs. We've been focused recently on scalable form factors, and this specification is in draft form. This is something that's available on our website, and we absolutely welcome your feedback. What we've designed is a scalable form factor that allows you to scale in the X, Y, and Z dimensions. So right now there's a lot of form factors out there, and we'd like to simplify that down and use a common mechanical form factor for all memory, I/O, and storage. One of the things that we get with this is now we can have a single wide or double wide type solution, and they can interoperate. You can plug a double wide into two single wide slots that are side by side, and it will simply work. If your board happens to have two connectors on it, you can take advantage of both connectors simultaneously. In doing so, you get incremental power as well as bandwidth. And because we allow multiple links per solution, you can bifurcate a connector to support multiple links. So this is designed from the start to be very scalable in all different directions. From a flash perspective, we can go up to 48 terabytes using today's flash. And of course, as we get more and more dense, you'll get more and more capability. We can support up to 5 terabytes of storage class memory, and that's based on our understanding of different storage class memory medias today. And we can support up to 280 gigabytes of DRAM, and that's a pretty big number, but now we don't have to have a customer pay for the highest density, highest cost DRAM to make that work. And that's 3.5 times the capacity what you would put into the DIMM. And if you ever had to manage DIMMs inside of a server, you understand why some of us would really like to move to this type of a solution. Because it's going to be so much more cost effective. It's going to make thermal management and several other aspects significantly better. And of course we can scale it up in the different dimensions to support different types of solutions. GPUs, FPGAs, you name it, we can support with this type of form factor, and it's all interoperable. And again, we eliminate the hard choices we have to make with the systems because we don't have to have mix match U.2, M.2, PCIe Chem, all the different flavors there. We can now just consolidate on one set of form factors and make that all interoperable across a series of enclosures. One of the things we have with servers is we have a lot of hard choices to make with how we package the different components and compute elements. Now we can actually pack our accelerators and our media together, or we can have all media bays. One of the things that this allows you to do is you can start simplifying your server designs. You don't have to figure out, how do I cram in a bunch of 300-watt GPUs into every server because I want to do deep learning everywhere. Now you can package them closer to the media itself. So now we can start thinking about creating memory-centric architecture where instead of going in and out of the processor for everything, you can go straight to the memory media. And whether that's storage class memory or DRAM or flash, you can now get to it directly. This picture illustrates again that we can use the new form factor. You can do this all on a single motherboard. We can do it where we can take a lot of servers and use the carriers in the front as an option. You can pull them out really easily. You can put in a new carrier, a new memory module, flash module, etc. that are all sharing that common carrier. And we can scale it up to rack scale by using any combination of active cables, passive copper, active optical, etc., and link those together to provide different levels of scalability. Composability, one of my favorite topics. You can look at today's solutions. The DDR technology, the high bandwidth memory technology, it's interlocked with the processor. Everything you want to get through that memory, whether it's processor core or I/O module, everything has to go through that processor. With GENZ, we can actually take that apart. The memory and the processing can work independently and can provision independently. More importantly, we can do that memory-centric architecture where we can put the acceleration near the data itself. So we can reduce the amount of data we move and the distance we move it. That's going to make us more power efficient, and it's going to improve performance. One of the things we can do is share the memory. Today, again, everything is owned by a single processor. You have to go through it. You can now create different units of memory out there. For example, with GENZ, we can interleave memory. This happens today in DDR. You can interleave across 4 processor cores within a system, and you interleave across, say, 4 memory channels, and that gives you aggregate performance improvements. And that's great, but the problem is that's only with that one processor. Now let's say I want to create a certain amount of storage class memory. One of the biggest issues we have from customers is they don't want that memory stranded, because the capacities we're talking about are measured in terabytes. So if we just take 4 of those scalable modules, that's up to 20 terabytes of customer data. You don't want that in a single point of failure domain. You don't want it to get stranded behind some platform that could fail and you're unable to get to it. Now at GENZ, we can overcome those limitations from a bandwidth perspective by interleaving that across a series of memory modules, and you have the ability to add RAID or erasure code type solutions to it so that you can survive any single memory module's failure. And in doing so, because we're interleaving, we get the benefits of aggregation. So let's say my storage class memory delivered 10 gigabytes a second of bandwidth, but I could do 64 when interleaving. That allows me to now get to 640 gigabytes a second, and I can make it to where memory is shareable. So whether you do dedicated portions of the memory to a given application, you can share it across it. You can now do that entirely within GENZ. You can't do that with any other technology. GENZ is economic in its ability to deliver right-sized solutions. What that means is that GENZ allows us to do for physical infrastructure what we've been doing with virtualized servers under hypervisors over the past decade. Now, instead of having fixed server configurations with static CPU, memory, I/O allocations, GENZ enables truly disaggregated infrastructure where CPUs, memory, storage, accelerators of all types can be composed into logical systems to apply to any workload. GENZ fabrics enable fabric-attached DRAM, storage class memory, CPUs of any size and computing capacity, accelerators, SSDs and NVMe drives, and gateways to legacy storage and networks. This architecture enables us to partition the infrastructure to create logical systems that are tuned specifically for the targeted workloads. This architecture helps us reach a point where over and under provisioning of infrastructure to workloads is a thing of the past. As the number of workloads increase, specific physical resources can be added instead of in a coarse-grained granularity of the past. If you need more memory, you're no longer required to add additional CPUs. The really cool aspect of this architecture is that the resources themselves can be partitioned into even finer grained provisioning. What GENZ is really enabling is a vision of what composable infrastructure should ultimately look like. The bottom line is that GENZ is economic because it really does right-size infrastructure for the best possible business outcomes. In summary, GENZ was created to simplify computer and data access architectures by applying memory semantic communications to everything. Though GENZ provides full OS and application software as well as mechanical compatibility, customers agree and welcome GENZ's ability to disrupt the status quo and unlock innovation within the industry. The GENZ Consortium is committed to creating an open ecosystem where all are welcome to contribute and benefit from the technologies it develops. We'd love to connect with you guys, so please come see us at these upcoming shows. We'll be at Flash Memory Summit coming up in August, and we'll also be at Supercomputing in November. As a full consortium, we are very open. We put everything out on our website. where you'll find the full specs that have been released. GENZ wants to make this the way that data centers are built in the future. And the best way to do that is to open it up completely to the public. So I invite you to check out the website, and who knows, maybe you can help define how tomorrow's data centers will work. Thank you.